is called the flying pant. These aluminum pants are going to go on top, and what it's going to show is a transfer of charge through conduction.
My phone is on. Let's just check this one first.
Can I have your phone number?
Okay, he's gonna call me right now. Here's the sound. Okay, you can. There you go. So right now I'm going to wrap this cell phone with this aluminum foil, and this is something that you can find in your kitchens. And I got this from a restaurant yesterday because I forgot bringing it from the restaurant.
Along with a couple of rolls.
And right now I'm making my cell phone. And can you call me again? Let me repeat one more time.
It's AT&T, it's a good network.
What's that? Reflecting 80% of the energy. Yeah. You should stick it in the shield too, the metal one, the cage. I was just going to indicate magnet induction.
Okay, let's try it again. So I wrapped it one more time right now. Thank you.
There's 3 reasons why oxygen, why we extract oxygen. Because first of all, because it's dangerous. Second of all, the oxygen can act as a conductor, and it'll eventually rob all of the oxygen from the graphite, piece of graphite, and it just won't work. So that's what's gonna happen.
Oh, cool.
Let it go more. All the way to my.
Oh. 2 months.
Go!
Fried it.
Yeah, let's go.
You fried it open?
Alright, it broke. But
that's pretty cool.
That is pretty cool.
The switch is off, which means that it's going to be an open circuit. The light will be on. But then when you turn the switch on, the light's going to turn off. And this is because electricity likes to find the shortest path to travel. If anybody can figure out what the circuit looks like, they will get a $5 Starbucks gift card. As you can see, it's constantly moving side to side. Now this is because it's constantly being pushed and repelled over 60 times per second, like I said before. Now this works because in a direct current, you're able to push and then repel at once because it's constantly in one motion. Now, in alternative current, because it's always switching motion, you're going to have it repel and attract really at a very fast pace, creating the illusion that the light is actually
a magnet. And I will drop this, and let's see what happens here.
It's
still in there somewhere around here. Should be falling by.
And is there any attraction between magnet and aluminum?
No, there's not actually.
So what's going on?
This doesn't have. It's not related with what's happening with this magnet, solar magnetic, and has a magnetic field of its own. And when we place it in when it's in the presence of a conductor like aluminum, it changes the magnetic field of this ball, which induces an electric current, as explained by Lenz's law. And this electric current creates a secondary magnetic field, which repels this initial magnetic flux in this ball. that the force created between the two magnetic fields pushes like basically slows the ball down. Now let's hold the jumping ring. There's some really exciting kids right there, but it's for all ages. It's not fun too. So here I have some rings. This is aluminum, copper, another aluminum, but this has a gap, and a smaller aluminum right here, and the light. So I'll be demonstrating how this works. So this is basically the same, pretty similar principles as the Faraday's and lenses law. This is a solenoid, copper solenoid wrapping, and this is an iron rod. So when I turn this on, hopefully, oh, let me put the copper one first. This is heavier, so I don't want it to fly too high. Right here. So it flows upward. The force created between the two magnetic fields propels it up. So copper is a conductor, but it's not magnetic. So normally it should not be. It's not magnetic, but that is very strong. Oh god.
To the table.
It stuck to the table, not the copper. Sorry. Oh my god. That is very strong. Jim out
So we'll be demonstrating the same concept of Lenz's law and Faraday as the greatest conductor. And these are just two strong magnets. And when they're put together, it goes slower. This is known as magnetic braking. And then I'm going to be showing jumping wires. Well, jumping wire. We're putting it in between it and to the point where it won't touch. Like nothing's touching each other. So right now it's off and you can see nothing's happening to it. But when the magnetic fields and the electric current interact with each other, you can see it move. Okay. This process also happens when I switch out the wires, and so the action is that they're induced in a conductor when the conductor is exposed to a changing magnetic field due to the relative motion of the magnetic field.
This was the last one. Thank you for coming.
Thank you. Oh, did anybody attempt to answer my puzzle?
Drinking Starbucks.
Starbucks guys, no.
Yeah. You guys sat down.